Hiya, it's Alistair back again, and in this video I'm going to show you how to create the electronics for not one but two different escape room puzzles which you often find. I've got them set up here, and the only difference between them is in a code change. So they actually require exactly the same electronics, which is an Arduino Uno at the top. This is a relay switch at the bottom which can power a maglock or whatever you want to happen when the puzzle is solved, make an LED light up or a display come on or open a door, whatever you want. And the key component that both of these puzzles have in common is a very small thing which I've got plugged into the breadboard up here, and it is a light dependent resistor, which I will try to show you there. It is a tiny little component that looks like that. And that is what I've got wired into the middle of this breadboard here. So the names that I give these puzzles, at least, the first one I call cover up, and the light dependent resistor there measures the amount of light that is falling on its surface, and it changes its resistance in proportion to that. So the less light there is, the higher the resistance, and the more light falls on it, the lower the resistance. That is measured by an input pin on the Arduino, one of the analog inputs. So if I cover up the sensor here, what you'll notice happen, hopefully, is that the light down there on the relay has switched on. So if you had some sort of load on this side of the relay now, that would now be activated. When I remove my hand, the relay goes off again. So off, on, like that, nice and simple. Now, that's not very exciting in its own right, so I kind of want you to imagine how that might be dressed up in a puzzle a bit more. So for example, if you placed this sensor here behind a picture frame like this, and what I'm going to do is I'm going to reset the puzzle, because in my code what I do is I detect the ambient level of light that's received on the sensor when the Arduino is first turned on, or when it's reset. And then if the light changes by a certain amount based on what it was reading when it first turned on, that's when it detects it's been covered up. So now that I've placed a picture over the sensor and I've reset the sensor, it doesn't think it's being covered up anymore. This is now its base level. But because a certain amount of light is still going through that surface, if I now cover up the eyes of that puzzle, you'll see the sensor goes on again. Off, on, off, on. So you can these sensors are relatively have quite a wide range of light levels that they detect. So by adjusting the value, the threshold in code, you can actually read through a thickness of paper or card so that the sensor isn't visible. Now I said that there were two different puzzles, so I've got essentially a variation on a theme, but can come up with quite a different puzzle result. So if I just upload one change to one line of code, what I'm going to do is kind of reverse the operation of the puzzle completely. So I'm still detecting the resistance provided by that LDR, but this time, instead of detecting when it's been covered and the resistance has gone up, I'm now going to detect whether the resistance has gone down because more light is shining on it. So I have here a pocket torch, ordinary torch, and now what you'll find is that the relay is off. If I turn the torch on and shine it on the surface of the LDR, oh sorry, my arm's in the way, I'll try and position my hand in such a way that you can see the light beam shining on there, the relay goes on. So for this puzzle, what players would perhaps find in the room is a pocket flashlight or a laser beam or any other light source for that matter, even a candle, and hold it up so that the light is detected there, the resistance goes down, detected by the Arduino, and that turns the relay on. Okay, so here's the wiring diagram for the puzzles I just showed you, and like I said, they share exactly the same electronic components, whether you want to do the puzzle where you cover up the resistor to activate the maglock, or whether you want to shine a light on the resistor to activate the maglock. It's exactly the same here either way. Now I've included the maglock on the load side of the relay here, even though I didn't have that in the video I just showed you. I've covered how to wire up relays in earlier videos, so if you want to know more about that, you can look that up. but this doesn't have to be a maglock. That can be anything you want. In the video I simply showed you how to make the relay activate to connect these connections to make any current flow on this side at all. So the bit we're really interested in, I guess, is simply all going on up here. There's very few components. There is literally just a light dependent resistor and a normal resistor. Now, when I've done puzzles in the past, I've used fixed resistors a few times, generally speaking to limit the current going into LEDs, just to stop them blowing out from receiving too much current. This time, however, the function of the resistor is a little bit different. Now, remember I said that a light dependent resistor changes its resistance according to the amount of light that falls on it. But the problem is that an Arduino cannot directly measure resistance. The input pins on an Arduino measure voltage. So if you have a digital input pin over this side, they will read either high or low as 5 volts or 0 volts, and the analog input pins over this side will read a value from 0 to 1023 according to how far the voltage on that pin received is between 0 and 5 volts. So how do we get from a LDR that changes its resistance to a 0 to 5 volt reading? And that's what the role of this other resistor here is for. So what I've created here is something called a voltage divider, or a potential divider. So we've got the 5 volt out from the Arduino going up this red line here, which goes across the fixed resistor first. Then it's connected to the variable resistor, which goes back to ground. But at the point in the middle between them, that's where we are reading our analog input pin. Okay, so it's somewhere between the two. And the reason why this works is because when you have resistors connected in series, the voltage drop at different points along the circuit varies proportionally to the value of the resistor. So, let me try and explain that another way. Let's say this resistor here is a known value of 10,000 ohms. And let's also say that with the level of light received on the LDR at a certain point in time, that also is 10,000 ohms. So they've got exactly the same resistance. If this is supplying 5 volts and this is ground, what we'd expect is that 5 volts would drop exactly half across the first resistor, and then the other half across the second resistor. So when the resistance of these two is the same, we would expect the midpoint between them to be exactly half of the voltage drop between the supply and the ground. Now let's say that the light level is reduced so that this is now 20,000 ohm resistance on the LDR, and the fixed resistor is obviously still the same. So now the split between them is 2/3, 1/3, and that's what we'd then expect to be able to read at the analog input there. So I hope that kind of makes sense, is that by inserting a resistor of known value in series with the resistor that is going to vary its value, and then measuring the voltage drop between them, we can sort of measure the voltage as a way of determining what the resistance of that must be compared to the fixed resistance. And then finally in the code, what we do is we map that to a certain value, and we'll say if it has risen or fallen this much compared to the base value, then we'll determine that the resistor has either been covered up or is having a light shining on it, and that will trigger the relay. So to make your voltage divider as effective as possible so that you can detect that full range of different values of light falling on the LDR, what you really want to do is choose the fixed resistor value that is going to be somewhere in the middle of the range of light values that you want to be able to detect. And that's going to vary from room to room depending on the amount of ambient light that you've got in the first place, depending on whether, like I say, you're installing the resistor behind a picture or a painting, or whether it's in the shadows in the room, somewhere else like that. So it is going to vary a bit from room to room. But what I can teach you is the way to determine the correct resistor value. So what I've got here is a multimeter, and I've got my light dependent resistor, which I've just connected there across the terminals. And then I'm going to set my multimeter to read the resistance that the LDR is currently detecting. Okay, so I've set it to the 20 kiloohms setting at the moment. So what that value here is telling me is that at the moment in the room it's detecting just about 730 ohms resistance in the room at the moment. Okay. Now if I cover up the sensor completely, what you'll see is that resistance rises. It's going up to up to nearly 20 kiloohms resistance when it's completely covered. And when I remove my hand, that will drop down again to about where it was. And then if I take my flashlight out again and shine it on there, you can see, or hopefully you can see, that resistance falling down to just around 200, 300 ohms. Okay, so I'm reading values in the atmosphere I'm in at the moment from around 200 ohms to around 20 kiloohms. So for the example in the circuit I just showed you, I'm using a 10 kiloohm resistor, which is around in the middle of that value and should get you a fairly good range of responses. It's worth 10 kiloohm is probably a reasonable starting point, but like I say, depending on the exact LDR you use and depending on the atmosphere of the room, you might want to vary that to get better performance. Okay, so let's take a look at the code that's running on the Arduino. So here we go. As always in code listings like this, I start with defining a debug conditional statement. That's going to allow me to output some information to the serial connection just to check what's going on. And then I define a few constants. These are values that are not going to change for the duration of the puzzle. So particularly I'm defining the pins which the different components are connected to. Now, the light dependent resistor has to be connected to one of the analog pins on the Arduino because we're going to read the whole range of values. It's not simply a digital signal of on or off or high or low. What we want is to record a whole range of resistances, and then depending on the value would determine whether the puzzle has been covered up or not. So that has to be an analog pin. The lock pin, that's the one that activates the relay, that can be a digital pin if you want. As it happens, I'm actually using the analog pin next to this one just because it makes the wiring more neat on the circuit board, so it doesn't have to be analog, but all of the analog pins on an Arduino can also give digital outputs as well, so I'm just using an analog A1 pin there. And now what I define is the base light level reading that the sensor detects when it's neither being covered up nor is it having a light shining on it. And I'm just initializing this to 512, which is a mid value. The analog input pins on an Arduino can detect values from 0 to 1023, so 512 is in the middle, but that value will actually change when the code first starts up and it will be calibrated to the light level in the room, so I'm just initializing that as a default. And then current reading will be the reading detected by the sensor each time we go through the program loop. And then this sensitivity value here, this is going to be the value that you can change to make the prop more or less sensitive, because when the current reading detected by the sensor has either risen above or fallen below the base reading plus the sensitivity, that's when it determines that the puzzle has been solved. So obviously if you want to do the cover up variation of the puzzle, what you'd expect is for the current reading to have risen above the base reading, add the sensitivity, Or if you want to do the shine on version of the puzzle, which is where you shine the light on it, you'd expect the current reading to have fallen below the base reading less the sensitivity. So we'll get onto that again a bit later. And pretty much all my puzzles, I have a puzzle state of where the puzzle is at the moment. Again, this is useful in debugging if you ever need to just report what the puzzle is currently doing at the moment. This function here, so this actually codifies basically what I've just described in practice. This just says, is the puzzle solved or not? And the variation that I've got written here at the moment, this is for the one where we expect the resistance to have gone down. So this is the when you're shining a light on, the puzzle gets solved. If you wanted to change this to the cover-up version instead, you'd simply change that to a greater than symbol and that to a plus than. And those are the only changes you need to make in the code. Everything else remains exactly the same for if you want the cover-up or the shine-on version of the puzzle. Here is my onSolve method. So this is called when the puzzle is solved, and I'm simply dumping a debug statement out to the serial connection, and I'm going to release the maglock by writing a value to the relay which is on the lock pin, and I change the puzzle state as well. And then I have an unsolve method, so if the player removes their hand and it's no longer covered up, or if they stop shining the torch on the LDR, then I simply reverse the solve method, so I write the relay back to high and the puzzle state becomes running again. So here's my setup function, which runs when the code first runs, initialize the serial connection if we're using debug, and initialize the pins. So the LDR pin is set as an input, the lock pin, which powers the relay, is set as an output, and it starts off with a high signal. You may need to modify that depending on whether you have an active high or an active low relay, but you can simply modify that and you just swap the lows and the highs around. Some relays are activated when they are sent a high signal at 5 volts, some are activated when they are sent a low signal, so it will depend on the exact relay you're using. So here's the main program loop. So we simply take a reading of the what's being read at the LDR pin at the moment. Remember, that's the middle value of that potential divider where the LDR is placed in series with a fixed resistor. So that should give us values between 0 and 1023. If we're debugging, I'm going to write that information to the serial connection. And then the next bit of the loop depends on what state the puzzle is currently in. When the puzzle started, it was set into the initializing state, and that's the state it will be every time it's reset as well. In which case, the first thing that happens is the puzzle is calibrated. So let's just go on to look at the calibrate method, which is down at the bottom here. So remember, right at the top of the script I said that I set the base reading to 512, which was the midpoint of the reading possible from the LDR. Well, this is the script that actually calibrates that to the true ambient light level in the room. So I define 10 samples and I read the value of the LDR pin 10 times, and then what I do is I divide the total from all those readings by the number of samples. So I'll sample 10 times what the resistance was and then divide by 10 to get an average reading of the LDR, and that is what I'm going to use as my base reading from which I will compare the current reading to see if it's varied or not. So that's what the calibrate method does. And potentially, I mean, currently that's called each time the puzzle is reset. You could also add a button if you wanted to remotely recalibrate that whenever you wanted, if there was a reason why the light level in your room changed or something like that. That would be easy to just call that method again at any point. So when the puzzle first starts, that method is called, and then the puzzle starts running once it's been calibrated. While the puzzle is running, the only thing that happens in the loop method is it just checks whether the puzzle has been solved, And remember that check if puzzle solved thing was just comparing the reading to the base reading. And if it has, it calls the onSolved method. And then if the puzzle has been solved, but the conditions for it to be solved are no longer true, so if the LDR is no longer being covered or if the light is no longer being shone on it, the unsolved method is called. Now, some puzzles you like to be what we call a latched solution, so once the puzzle has been solved once, it remains solved forever. If that's the case, you can get rid of this bit here. Other puzzles, it's nice to have it that the player must continue to input whatever action it was that solved the puzzle, or else it becomes unsolved again. So that's what this allows you to do. If you want a latched puzzle, you can simply get rid of that, and the first time that the puzzle is solved, that method is called, and then from then on it will just remain in that state. So that's about all there is to say about these puzzles. Like I say, they're quite popular in escape rooms, and it's very, very easy to dress them up in different props to make them fit your theme and your narrative. And they really only require one single component. This little LDR here is what powers the whole thing. The total cost of components is probably, for what you see on the board here, under £10. Depending on what you're powering on the other side, you might need to buy a maglock or something as well. But it's really simple, very flexible. If you'd like to access the wiring diagram or the code listing or the additional documentation where I'll tell you exactly where I bought all of the components I've used, please follow the link below the video to my Patreon page, and you'll find all the details there. Thanks very much for watching. Bye.